Hello, this is Professor Dan Kernler of Elgin Community College back with another video in my statistics series. In this video, we're actually going to look at M&Ms. All right, today we are actually in my kitchen of all places because we are going to be counting M&Ms. Now, I just got to give fair warning here. I have one shot at this, so if the video ends up looking screwy, that's because I only had one take with lighting and only have so much time in the day to get all this set up. The idea is we want to count the actual ratio of the different colors and then compare that to what we would expect if the proportion is the same as what the company expects. So the only way to do this is to open up this bag, dump them all out, and start counting the colors. All right, here we go. Oh, that is a lot of M&Ms. Oh, this may have been a bad idea. I'm going to be counting a long time. All right, let's start sorting these. Oh gosh, that is so many M&Ms. What was I thinking buying this huge bag? Oh, they smell so good. I want to eat them, but I can't eat them until I've counted them. To me, it's looking very suspiciously like an equal amount of each one. I'm going to call that 49 with those two halves. Okay, 49. 53. See, it's interesting. They're like almost all about the same. 57. 60. This is crazy. We keep like increasing. Was I like doing something subliminal where I started with the smallest ones and kind of glanced at them and like worked my way up? What the heck? That's weird. No Rain Man, that's for sure. Okay, that is odd that each one had more than the previous one. But there you have it. There are the counts. All right, so now we need to get to the computer and compare these versus the proportions that we were given. Now, I think what I want to do is I want to actually compare these. What if we assume they were all the same? They should have been all the same. Let's compare those as well. The best part is now that I have the counts, I can eat some. All right, let's get to the computer. All right, I have one other detail I forgot to mention now that we're back in the studio. So there are two different plants that make these M&Ms, and apparently the story is that the proportion, the color distribution depends on which plant. There's an old blog from the statistics company SAS, S-A-S, I'm sure it stands for something, but they have these two different sets of proportions. The M&M package that I looked at happens to be from the HKP. It has HKP stamped on the bag. So what we're going to do is we're going to test, do our proportions, do our counts meet what we would expect if the proportions are according to that distribution. So I have my observed counts from up in the kitchen. For the expected, what we're going to do is take the total, I believe it's 346, and then multiply by that expected percentage from the previous 2017 numbers. So for the red, it's 346 times 1/8. That's 43.25. For the orange, it's times a quarter. And then I think the only other one that was a quarter was blue. The other ones were all 1/8. So now we have observed counts for each one, the actual counts in the M&M bag, and then what we would expect if they followed those 2017 numbers. All right, you know the drill. If we're going to test this, we need a test statistic. So we're going to do another chi-squared. It's an observed versus expected. So observed minus expected squared, divide by the expected, and then add all of those up. Follows the chi-squared distribution with k minus 1 degrees of freedom. Here, k is the number of categories. So for us, that would be 6 categories. So we would have 5 degrees of freedom. It's the same as the other chi-squared distribution ones where we have to have all the frequencies at least 1, and no more than 20% of them can be less than 5. If those conditions aren't met, what we can do is combine some categories until they are. Let's go through the hypothesis testing process. We have a null hypothesis here is that the proportions meet those 2017 ones. And then the alternative would be that they don't. Our level of significance, alpha, 0.05. The test statistic, that's this chi-squared test statistic. So let's pull up our colors here, kind of zoom out a little bit, give some workspace. Our chi-squared for the first one is 61 minus 43.25. Square that over 43.25. So observed minus expected. Square that over the expected. And the same thing for the orange, for the yellow, for the green, the blue, and the brown. And we get a total of about 49.5 for our chi-squared. You can also do this in StatCrunch. You do have to manually compute those expected values. That's the total times the percent you expect in each category. I have those in here. And then it's just stat, goodness of fit. And then we're going to choose the observed, and you have to pick the column. So that's our observed column, and then expected column. That's in the expected column that I've already typed in. Hit compute, and we get the same 49.5. So we have our test statistic, 49.5, our p-value from the StatCrunch output there, less than 1/10,000. That's super rare. That means we reject the null hypothesis, which means pretty obviously that there is enough evidence to say they don't follow those proportions, right? It seemed to be that they were all the same or pretty similar, right? Well, actually, I redid this like, well, let's test that. I wonder if they're all the same. Let's see if we can prove that they're not all the same. So the null hypothesis here is that they're equally distributed. Remember, the null hypothesis has to be what you assume is true, and then you have to prove like a difference from that. So the other option is we could assume they're all equally distributed. Then the alternative would be that they're not equally distributed. Same alpha. The test statistic is still that chi-squared. In StatCrunch, I don't know if you noticed it. If we go options edit from our previous results, there was another option as we could say they're all in equal proportion. So they're all evenly distributed between the different categories. When we do that, we get a much smaller chi-squared. It's only 3.18. The p-value here, very big, 0.6724. So now we would not reject the null hypothesis. That means we don't have enough evidence to support the claim that they're not equally distributed. Now, for those who are skilled with English grammar, you might be a little like, wait, we're not enough evidence to show they're not even, why can't we just say they're equally distributed? That's one of the peculiarities of hypothesis testing. I can't prove they're evenly distributed. All I can say is that I can't prove they're not equally distributed. Now, maybe they are. It's certainly reasonable to say that they are, but we can't prove definitively that they all have 1/6. They're all produced at 1/6 of the total. We can't prove that. We just say, hey, they probably are. We can't prove that it's different from that. I mean, maybe it's 1/6 would be about 17%. Maybe one's 15%, and one's 18%, and one's 16%, right? Maybe they're all really close to that. And so we didn't get enough difference from that. We can't prove that they're equally distributed, but it certainly seems like they are. They're very different from the 2017 proportions for sure. All right, I want to finish with a little more serious example. I want to go back to that discipline data. We've analyzed this a variety of different ways. I want to show you yet another way to analyze this. What I have here is I have a column, and I have the race or ethnicity, and I have the counts, the total number of discipline referrals for each of the groups. We can then find the proportion of those disciplined. So here are, of those disciplined, here are these proportions. Now, you might look at this and say, whoa, look at that, Hispanic Latinx are hugely disciplined, but maybe they're just a big part of this population, right? You have to be really careful. So what we want to do is compare these proportions of those disciplined, what proportion are from each race or ethnic group, and then compare that to the population. So here's the proportion of the population, and you can see now we have some groups are overrepresented and other groups are underrepresented. So what we're going to do now is compute what we would expect as the count if the proportions followed the number from the population. So there's 4,277 total discipline referrals. And so if we take those and multiply by the proportion that each group is of the population, here's what we would expect for each group. if they followed the same distribution as the population. Now then, we have an observed versus expected, and we can do a test. The null hypothesis here is the distribution for discipline follows the distribution of the population. And the alternative would be that it does not. Alpha, the level of significance, we'll use 0.05, test statistic, that's our chi-squared. I actually have that output here for you from StatCrunch. We have the actual counts, and then I typed in the expected counts. Here we get our chi-squared goodness of fit test, and you can see very big chi-square, very small p-value. So our chi-squared is 512.9, our p-value less than 1/10,000th. That means we would reject the null hypothesis, and there is enough evidence to support our claim that the discipline rates don't follow the distribution of the population. And again, that's not a surprise. We've seen this repeatedly. No matter how we looked at those data, it always showed that the race or ethnic groups, it mattered. It made a difference. They weren't distributed the way we would expect if there was either no bias or no actual behavior differences based on race. All right, that is it for this video on the chi-squared goodness of fit test. I hope it helped you understand it. If you're interested in seeing more, you can subscribe, hit the bell to get notified. As always, thank you to the Elgin Community College Board of Trustees for supporting me by approving my sabbatical for the spring 2021 semester. Thank you so much for watching, and I will see you in the next one.